Okay, so we're going to continue with 5.8. So this is 5.8b. We're going to look at turning points into maximums and minimums. We're going to define turning points as the maximums and minimums. I can't say it, but I can sure find it. We're also going to use our calculators today. So we're going to build on what we did before. Let's think about, and I've started this sentence, polynomial functions have at most, and let's see. If we said y equals x cubed, and then we said plus 2x squared, I really don't know, I'm just making this equation up. We do know that this is a polynomial function. It has exponents that are positive integers. And we know the end behavior is Saturday Night Fever in opposite directions. And so this function looks something like this. So this is a degree 3 polynomial with 2 turning points. This is increasing and it changes to decreasing. That's a turning point. It changes the direction of the slope. Even though we don't consider this to be one slope like a line, this has changing slope all the way up the function. But it's definitely an increasing function. It goes up. Then it goes down, that's decreasing, and then it goes up again. So we're going to call this increasing, and we're going to call this part decreasing. What I really want to define is turning points. So this has 1, 2 turning points. 2 turn points. And I'm not just calling them minimums and maximums because A, that's too hard to say. But B, turning points tells you exactly what's happening there. When we get into pre-calculus, we're going to call these extrema. That mean the extreme value of the function. So this is the highest point in this neighborhood, and this is the lowest point in this neighborhood. And we'll call them extrema for extreme values. But anyway, what do you notice so far? The second example, let's say we have y equals x to the 4th plus I don't know what. This could look like a w. It could look like a w that is not equal or symmetrical. It could look like this kind of w. It doesn't really matter. We do know that x to the 4th has the same end behavior, and this is a positive x to the 4th, so they both go up. And how many turning points does this have? X to the 4th is decreasing, this is a minimum, then increasing to a maximum, and decreasing to a minimum, and then it goes up forever. So this is degree 4 with 3 turning points, or extrema. So polynomial functions have at most, we call this n minus 1 turning points, where n is the degree. And that's just another way to help us graph things. So let's look at another couple of examples before we pull out our calculator and find exact minimums and maximums with our calculator. So let's say that we have this function here. It's going to be g of x equals 2 x minus 1 squared times x minus 4. And we learned in our last lesson that we have 2 zeros. We have zeros of positive 1 and positive 4. These are also x-intercepts or solutions, whatever you'd like to call them. They all mean the same thing. This has a degree of 3 because this is squared, so x squared times x is x cubed. So it's going to look like this. This 2 in the front is not a 0. It does stretch our graph by a factor of 2. And we learned that this 2 means it has a multiplicity. It's going to bounce at 1. Okay, so let's give a quick sketch for this. 1, 2, 3, 4. I have a 0 at 1 and 1 at 4. And I know that I could find some points to help me out. I know that my end behavior is going to be up and then down, but maybe I need some other values like the y-intercept. Y-intercept means that the x value is 0. So if I plug that into my equation, I'll have 2 times negative 1 squared. 0 minus 1 is negative 1. And then 0 minus 4 is negative 4. That's going to give me 2 times 1 times negative 4, or negative 8. So I've got 1, 2, 3, 4, 5, 6, 7, 8. So this graph is not to scale because my x scale and my y scale are different. And what else could I say? Well, let's see. I know basically it's going to look like this, and at 4 it goes through, and it's going to bounce at positive 1 and go through this point here. I have an idea of what it looks like. So I've got one turning point here and one turning point here. Note up here it says at most n minus 1 turning point. So this is a third degree, and I have 2 degrees, 2 turning points. So I've covered that rule fine. But where is this minimum value? Let's see if we could find this value in the middle. So what would that be? That would be 2.5 or 5/2. And this is helpful for estimating things on our graph. We're going to use synthetic substitution to figure that out. So I'm going to estimate that 1, 2.5, 5/2 is where my minimum value is. I multiplied out the original problem so I could use synthetic substitution. 2, negative 12, 18, and negative 8. That would be 2 when I bring it down. 5/2 times 2 is 5. So that's negative 7. Negative 35/2. It doesn't always work out pretty. So what is that? 36 minus 35 is 1/2. 5/2 times 1/2 is going to be 5/4. And then that's really going to be negative 8. So that's negative 32/4. And 5/4 would be negative 27/4. So that's going to be 6 3/4. Negative 6 3/4. That's what I'm going to estimate this to be. So I'm going to change this to be 1, 2, 3, 4, 5, 6, and a 4 here-ish. And it's round, okay? This is not an absolute value graph. It has to be round there. So I just estimated, okay? So this is really 2.5. It should be sort of underneath that one. And I have a pretty much to scale graph. I have the zeros, I have the end behavior, I have a y-intercept, and I've estimated this. So this is an estimate of the minimum value there. So this would have what's called a local maximum. That point is right here. It's the highest point in this neighborhood of points. It's not higher than this point, but it's higher than all the points around it. And so this point at 1, 0 is our local maximum. And we're estimating our local minimum to be, minimum is an N, so silly, to be about 5/2 negative 27/4. Okay, so it's an estimate. And we've done that in class before. You would need to use this for your polynomial project, and that gives us a nice, more to scale graph than I had without trying to figure that out. So now let's do the same thing with our graphing calculator. So find your calculator and let's do some of this math together. So on my calculator, I'm going to use this same function. So I'm going to type it in just as it was given to me with the 2, and I can type in parentheses x minus 1, parentheses, squared, and then parentheses, x minus 4. And I could graph that. I can also graph, just for fun, just to make sure that I did this part right. Let's see if I have 2x to the third power. Don't forget this little caret symbol will give you to the third power. But I have to get out of the exponent to move on. Minus 12 x squared plus 18x minus 8. So when I graph this in a standard window, so zoom 6 for standard, it looks like my graph. And this is a little bit further over than 2.5, but let's see how far down it goes, okay? So I still have a maximum here at 1, 0. I have the same end behavior, and I have this y-intercept, which I can check over here. So we're going to find the maximum value. To do that, we're going to use this menu, which you see up here. I got here by pressing the blue second button and then trace for calculate. So again, if you go second and then trace, it takes you to the calculate menu. And you can see C-A-L-C here for calculate. That will help you remember how to get there. It's blue, so you push the second button. Anyway, we're going to do a maximum first, so 4. So now the calculator asks us a series of questions. It wants us to narrow down what we're looking for because the calculator only does what we tell it to. It doesn't know any more than that. You can't shout at it, hey, find me the maximum. You have to answer these questions. So left bound. So I'm looking for this point, and I am on the left. So I'm going to hit enter. Then I'm going to move my cursor past the maximum to the other side. It doesn't matter where you are on the other side because when you hit enter, it's going to say, okay, I'm looking in between these two lines. You can make a guess if you want, but there's only one maximum here, so I don't really have to. But if you feel the need, you can arrow closer to the maximum and hit enter, and it will find it. Now, I said the maximum was 1, 0, and they've got negative 1.33 e to the negative 14. Does that mean the same thing? I said the maximum was at 1, 0. So it is the same thing because they're just saying scientific notation. There are 13 zeros here. When we move the decimal this way, it's going to have all these zeros and then 133. The calculator has its limitations, and this is one of them. We will be able to find some maximums better than the calculator can because we're using just regular math. We're not doing like a process and then a process again and over iterations until we find the maximum. We're actually finding it purely by math. So we win. And the maximum's at 1, 0. Let's find the minimum. So again, we use second trace. So I'm going to still put 1, 0 here. And if we go second and then the trace button, this time we're going to choose 3 for minimum, or you can arrow down, either way. And again, we have to be on the left of it. So I'm going to move, so I'm looking for this point, the minimum point. It tells me minimum is what I'm looking for, so I won't forget. And I want to be on the left of it because that's what the question is. I hit enter. Now I need you to move to the right of it and hit enter. And it's made these two lines. It's looking for a minimum value in between them. I can hit enter and it will find it. So this value is at, and we're going to round to 3. So minimum value is 3 for x and negative 8 for y. So it's more than what I found because I had my point here and they have a little bit bigger graph here, and so it went down further. But this graph was better for me finding this point because before, you can see I have this little tiny, this was what I had graphed originally. This one is better. So it wasn't perfect. It was an estimate, and the calculator can tell me exactly what it is. When you get to calculus, we will find these points exactly without a calculator, and we'll do a better job than our calculator, just like we did with the maximum value here. So What you can do is you can type in your equation exactly as it's given to you in the y equals, and then graph it, and then look for those minimums and maximums. Let's do one more. Okay, the second one I want to enter into my equation is f of x, or y1, equals x to the fourth plus 3x cubed minus x squared minus 4x minus 5. I don't know what the zeros are. It's not factored. I'm not going to try to sketch this in advance. I do know that it has end behavior that looks something like this. So probably I'm looking for two minimums and a maximum. So type this in your equation, in your y equals, and let's graph it. X to the fourth plus 3x to the third. Don't forget to come out of your exponent. Minus x squared, minus 4x minus 5. X to the fourth, 3x minus x squared minus 4x minus 5. Okay, so when we graph this, there's my w. Mine will graph a little bit faster than yours. And we're looking for a minimum and a minimum and a maximum. We have two relative or local minimum values, and we have one relative or local maximum value. So it's up to you how you want to find them, but you could make yourself a list that says minimums, and there's going to be two of them, and then maximums. So they're relative. It turns out that this is actually the absolute minimum because my function on this side goes up forever and up forever on this side. So this does have an absolute minimum, and this would be a relative minimum. But I'm going to put relative for right now. So we're going to do second, calculate. I've got minimums first. So minimum is 3. I'm just going to type in some numbers. I can type in -4, and it will give me that line. And I can type in -1, tiny negative, and it will give me the line. So I don't have to use the arrows to move between. I don't have to guess because I did a good job. It found the minimum. The x value, let's keep 2 decimals, -2.28. And the y value, -9.61. So -9.61 is the lowest this function goes. I can find another minimum, so second, calculate minimum. I don't want to use this as a left bound. I guess I could. No, I can't. It would be lower than this one. I need to say something like 0. So 0, enter. And then I can say 5. Anything on the other side is fine. It's going to look in between these for this lowest point and enter. And this value is 0.68. Make sure to round nicely. And -7.02. And then maximum works the same way. So second, calculate maximum. So 4. Oops, I entered too soon. 4. So left bound, I need to be on the left. So let's say -1. And then I could say 0. And I get the maximum as -0.65 and -3.47. Okay, so easy as that. Use your calculator to plug in. We've got one more example of a thinking problem, so let's do this together. I'm going to move my calculator for a minute and just work on paper for a sec. Okay, so this is an example of maximizing a polynomial, making a model out of something. So far, it's just a rectangle, so it's not very exciting. I need you to pretend for a minute, maybe you're doing something Science Olympiad and you have to build. Let's say that we've been given a piece of cardboard and it's flat. And we know that the dimensions of it are 16 in this direction and 20 in this direction. So it's 16 by 20. Now our goal is to make a box without a top, so a bottom and 4 sides that will have the maximum volume. So what do we know about that? First of all, we can't make a volume out of this flat piece because that's nothing. It won't hold anything. So what we're going to do is we're going to cut out sections out of the corners that are X. These are squares. So both directions are X. So this is X and this is X. And this is the same X. All the corners have the same piece cut out. And then we're going to fold along these lines, like we're going to throw this piece away. And this dotted part is the new base, and we fold up this side and fold up this side and tape them together. It will make like the bottom of a donut box, for example. Okay? So what we need to do is we're trying to maximize volume. So we need to find the X value that gives us the maximum volume. So how do we do that? Volume is a measurement. How do we find, what's the equation for volume? So length times width times height, right? It's a three-dimensional, if this is actually in inches, this would be inches cubed when we multiplied it out. So this is what we need to do. We need to figure out how to make an equation that's not L, W, and H, because I cannot put that in my calculator, but that represents the 16 and the 20 and this X that makes sense. Okay? So I don't know how big X is. I could cut out little tiny squares and have little tiny short sides, so it's like a donut box. I could make X really large and cut out big sections so that I have a very small inside and really tall sides. So that's what I don't know. I need to figure out how to make X be a maximum. So what I do know is this. If I was to make my box, then it would look something like this with an inside. That's not bad. So I'm going to fold up this amount. So I know that this is X. Okay? What I need to figure out is how long this side is. It started off as 16, but I'm cutting out these squares. So I'm going to have 16 to start with, but then I'm subtracting those squares. So how much is this length when I subtract out an X here and an X here? It becomes 16 minus 2X. Because I took off an X piece here and an X piece here, and what's left in the middle is 16 minus 2X. That means that this side is 20, also subtracting 2X. So 20 minus 2X. So now that I've made it a 3D sort of looking shape, I can find volume. The volume equation is this side, 20 minus 2X, times this side, 16 minus 2X, times the height, or X. And my box could look a whole bunch of different ways. So it could have a very small bottom. Shouldn't draw that side. With it really big sides like this. But it would be smaller this way. Okay, that was bad. But this X is what changes. And it also shrinks these sides. So before I even graph this, what's the smallest X value we could have? So X could be 1. We could subtract 1 from each side. This will be 14 then. What's the most we could subtract and have any volume? So it has to be, we'd have to do more than 0. So we're not going to include 0. And we're not going to include 8. Because if we subtract 8 from both sides, we have 0 here. And then we still don't have any volume. So it has to be a number smaller than 8. It's probably not 7.9. It's probably somewhere inside of that. But I'm not sure. But this is how domain works. I can't have x bigger, like I can't have x to be 10 because I can't subtract 10 from both of these sides. So it's just something to consider. When I put this in my calculator though, the calculator doesn't know that I'm trying to make a donut box. So it will graph this whole equation even past 0 to 8. But let's look at what that graph looks like. So I'm going to make this a little bigger. There we go. I'm going to plug this whole equation in. I'm going to write it just like it is. I don't need to multiply it out. 20 minus 2x, parentheses, 16 minus 2x, parentheses, x is the height. So it is a cubic. It has x times x times x. And when I graph it, I can't really see it because it looks like straight lines. So let's zoom out. Let's change the window to be the x value, negative 10 to 10. That covers my 0 to 8. But let's make the y maximum something really big and see if we can see it. There we go. I can't really see the other dip here, but that's okay because this other dip is too much. I can't subtract this much. You can see that 0 is the beginning boundary for what I could subtract out, and 8 is the other boundary on the other side. So that did work out. Now let's try to find this maximum. Where we find this max is the x value that we need to cut out of our box. So we just did maximum. Second, calculate maximum. 0 is fine. On the right, I need to be somewhere like 8. And it's going to find the max in between. So the maximum x value, the part that I can cut out, needs to be a square that is 2.94 inches from either end. And if I do that, then my volume is going to be this y value equals the volume equation. So if I do all of this, what I get out is volume. So volume and y are the same thing. So this is the y equals, in my calculator, volume equals 420.11 inches cubed. That would be how much my box would hold. And if I cut out less, I'll have less volume. If I cut out more, I'll have less volume. And if I cut all the way out to 8 inches, I would have 0 volume. I can't have negative volume, so those values are not important to me. I don't really need to see more in the negative. I don't need to see more here because I can't have negative volume. It doesn't work for the context of this problem. So you have some other things to look at, some problems like this one in your homework. So watch this video again if this part doesn't make sense to you. The idea of I want to cut out areas from my piece of cardboard, and that changes what this width is and what this width is because we did cutouts. So think about this problem when you look at some of those word problems. All right, there you go, 5.8, using the idea of turning points, minimums and maximums, the idea of increasing and decreasing, and we looked at how to find it on your calculator. All right, thanks guys.